Welcome for this presentation about IPv6 autoconfiguration, which enable plug-and-play devices, which is a very important feature for IPv6 because it enables any device to be operating without any configuration from the user during the whole life of the device on the network. You will see that it is not only actually the configuration when the node is joining the network, but when you may have any change in the configuration, this will be also automatic. And also with mobile IPv6, we will see that it will be possible to keep the same configuration while you keep moving, and so you will not have to log out or log in. You will remain connected all the time with your home configuration. So that's a little bit about myself. So I'm in the industry for about 15 years. For IPv6, 20 years for TCP/IP and Cisco. I'm a ccie. I'm a certified IPv6 forum engineer and trainer. And you can find me on the internet, ask me any question, or follow me on Twitter, on blogs. I will be happy to answer any question. So autoconfiguration, again, this is not only for the configuration at startup, but if, for instance, you need to renumber because you got a new prefix and the whole building must change its address, or if for security you must change your address every day. This is also what we call autoconfiguration. And also for device roaming, we will see that with mobile IPv6, you can keep your configuration all the time and stay always connected. There is an exception for autoconfiguration, which is enabled by default for most platforms. This is with Linux. With Linux, you may have to do some manual configuration to enable it because it may not be configured by default. So when you start autoconfiguration, basically an interface which is just starting, the first mode will be tentative mode. In tentative mode, basically the interface is going to try to get a linked local address, and if it is not able to find a linked local address, then the interface will be disabled for IPv6. It is going to perform duplicate address detection to make sure that this address is not a duplicate. If the linked local address is found unique, then we can go to the next level and find some more configuration, some more addresses. So the preferred state for autoconfiguration is the preferred state. In the preferred state, actually, the address can be used for existing and for new connection. So this is a normal mode, and as long as your address is refreshed by a router advertisements or by the DHCPv6 protocol, then your address may stay preferred forever and will be used all the time. Now, if you fail to refresh your address may reach the deprecated state. In this state, this address should not be used for new connection. It should only be used for existing connection, but not for the new one. So this is actually something which could be useful when you do renumbering of a network, and in a transition phase, the address can be used for existing connection, but not for new connection. The valid state is actually the state which is the sum of preferred and deprecated. This is actually the time where the address could be used, with a small difference between preferred and deprecated, but basically the address can be used. But if the address is not refreshed by any means, then it may reach the invalid state. So in the invalid state, the address cannot be used anymore, and it is actually as if the address was removed from the interface. The address is finished and cannot be used any longer. So that's the flowchart of a node which is starting. The very first step again is to derive a linked local address from the prefix FE80 and an interface ID which is normally derived from the MAC address. And you send a neighbor solicitation to the solicited node multicast address of yourself, and sending a packet to yourself, you do not expect somebody else to reply with a neighbor advertisement. If somebody replies, it means that the address is a duplicate, and if the address is a duplicate, we stop the process, and the interface will be disabled for IPv6. It will not be used. So that's the very first step. Check that we can have a linked local address and verify this address is unique. So this is a capture of the process, so you can see the neighbor solicitation packet. So the interface does not have a source address yet, so it is the source address is not set at all, and we have no neighbor advertisements received, so the address is unique. And because the address is unique, we can go to the next step, which is to send a router solicitation message to request router advertisements to get some configuration from existing router. So this neighbor solicitation is sent to the solicited node multicast address, and you can see it here on this capture. So once the linked local address is found unique, we send the router solicitation packets, and we expect to receive router advertisements. If we don't, then we are going to try DHCP version 6, and we exit the auto-configuration process. But if we receive router advertisements, we can initialize the interface and maybe configure some more prefixes, some more addresses derived from the prefixes which may be announced in the router advertisements message. So that's the second step of the process. Just send a router solicitation, expect a router advertisement to get some configuration to perform auto-configuration of the interface. So that's not a good idea if you think that blocking the router advertisements, you are going to force DHCPv6. Actually, if you want to use DHCPv6 in IPv6, you must set some flags, and that's the way to do it, because you need router advertisements on a LAN. For instance, DHCPv6 is not able to provide a default route. So you always need router advertisements on a LAN, and not a good idea to disable it on a LAN to force the use of DHCPv6. On Linux, again, you may have to configure the fact that the router advertisements are accepted by the Linux platform. If you don't, it may not be accepted. It may be rejected. It may be good, actually, in some case, in some data centers when you don't want to rely on anything automatic because you want to make a very solid, robust configuration and make sure that nobody could send some rogue router advertisement, for instance, and break your host. The router advertisement contains many kinds of information. First of all, the router advertisement contains information if this router must be a candidate for a default route. So it will depend if the lifetime is greater than 0 or not. The lifetime parameters only applies to the capability of the router to behave as a default router. You may also have the preferences if you have many routers, so the router with the highest preference will be the default router. You also find the MAC address which is provided, so you don't need to request it with a neighbor solicitation. You also find some important parameters on in the router advertisements, like the default hop limits, the MTU of the link, the parameters for the neighbor unreachability detection, the address of the DNS servers can be provided as well, and eventually a list of prefixes which can be used to derive addresses. Then finally, we also find some flags which actually tells the workstations if they need to also use DHCPv6 to request some more configuration. So that's a capture I took from my connection with my service provider. So you can see the router advertisement with the lifetime of 1,800 seconds. So which means that I need to receive another array before this timer expires, or the default routes will disappear. The reachable time and the response timer are set to 0, which does not mean that we must set these values to 0. It means when it is set to 0, it means don't touch it. Just leave it the way it is configured. Don't touch it. That's all it means. Here we find also a prefix which is announced. We see that with this prefix we have flags with some bits, the on-link and the autonomous bits. And so we also find some timers, and we will see that these timers and bits are very important for stateless address auto-configuration. We can find also some DNS servers addresses, the MTU and the MAC address of the routers. The router advertisement is sent to the all IPv6 node multicast address. Also, in the router advertisements, we may find a list of prefixes. So, in this list of prefixes, each prefix comes with some flags and some timers. The on-link and autonomous bits must be set for the prefix to be used to derive an address or to refresh an auto-configured address. Also, the preferred timer should not be bigger than the valid. The valid should be greater than the preferred, otherwise the prefix is ignored, and the valid should not be null, because otherwise the prefix will not be used for stateless address autoconfiguration. If all these conditions are verified, then we derive the address from the prefix and the interface ID, which can be randomly chosen or derived from the MAC address. And again, we perform duplicate address detection, which is to send neighbor solicitation messages to the solicited node multicast address, which is basically we send a solicitation to our own address, and we don't expect somebody else to reply. Otherwise, it means that the address is already used by somebody else. And in this case, we are not going to use this address, but the address will not be, the interface will not be disabled for IPv6, as it is the case for a linked local address. So we looped until we have no more prefixes to check in the list. So again, each prefix has 2 bits which must be set if the prefix must be used to derive an address with stateless address autoconfiguration, and we also have two timers which will determine, so we have seen the preferred and the valid lifetime. What does it mean? So this is how we set these values when the address is configured, and also afterwards this is used to refresh the address from which is derived from this prefix. Again, on Linux, this is something that we can configure. The prefix information could be ignored if we don't configure it to be enabled. So this is again something which in Linux must be configured and is not fully automatic. So we said that we derive the address from the prefix, and then we build it using the interface ID. Again, the interface ID may be derived from the MAC address. This is the EUI64 format, or it can be randomly chosen, which is a privacy extension, which is there actually because with IPv6 we don't have NAT, so we may be identified by our address on the internet, and if we don't want to be identified on the internet, we can change our address every day and build the interface ID randomly. The final check from the router advertisement is to check if we must use the DHCPv6 server or not. If the managed address configuration flag, then we use the DHCPv6 to configure everything else in addition to what has been already configured, so which means addresses, servers, domain name, whatever. But we can also use the DHCPv6 for everything but address. This is because the router advertisements may not contain all the information we need, and we may not need to use the DHCP to get an address, but we may need it to get some information from the DHCPv6 that we cannot have from the router advertisements. So that's the last step of the process. Again, verify if the IPv6 must be used or not. And this can be done again using the managed and the other configuration. So when the managed flag is set, actually we use the IPv6 to configure address and everything. And the O flag, the O bit is actually redundant, but it is a good practice to set both when we need both, just to make sure that in case an implementation is not very conform to the RFC, we just use the IPv6 to configure everything. When the O flag is set only, it means use the HTTP, but only for prefixes, for servers, not for address, but for servers and for domain name, for instance, but not for address, not for any prefix, for instance. DHCPv6 cannot be used to get a default route. So again, we cannot rely only on the DHCPv6. So we have many different kind of modes for IPv6. So stateless address autoconfiguration, we don't need any DHCPv6 server. We have the stateful DHCPv6 when we use the DHCP to get address and servers information, for instance. And we also have the DHCPv6 prefix delegation, which is a mode existing in IPv6 and not in IPv4, which permits to allocate a block of address and not an address. And then this block can be received by the client and then be subnetted to configure many addresses, many interfaces. So that's the stateless address autoconfiguration again. So we send a router solicitation to get the prefixes. From each prefix we derive an address, and then we use DAD to check that the prefix that we have configured is really unique, because it is the interface ID can be chosen randomly, and in this case, so it is good to check that the address is unique. The stateful DHCPv6 autoconfiguration, here, in addition to what we have seen from the stateless address autoconfig, we also use the DHCPv6 to get an address. So this is why it is stateful, because actually the DHCPv6 only keeps a state when it allocates an address. Just in case the client is going and the server, if it does not receive any renew, it will send a message to the client to say, hey, Mr. Client, do you want to keep this address? And if the client fails to reply, the servers know that the client has gone, and the address can be reallocated for somebody else. So that's why, in this case, the DHCP server keeps a state, and it is a stateful DHCPv6 autoconfiguration. In the case of stateless DHCPv6, again, the address is allocated using stateless address autoconfig from the router advertisement, and then DHCP is only used to get some additional information like DNS address, prefixes, whatever. And also, very important, the prefix delegation. So again, with prefix delegation, you do not allocate an address or give any server information, but you actually have a server which has a super block, and for each client which is requesting a block, it will allocate a block. So here in this example, the server has a /32 block which is ready to allocate a block /48 block for each client. And then this /48 can be subnetted for each interface, and the downstream interface can configure host with stateless address configuration, just like we always did before. So this is a full example of, I like this example because the CPE here is a DHCP PD client and the DHCP stateless server. And the PE here is a PD server, or it could be also DHCP relay if it is not providing the DHCP function itself. So the CPE actually here is sending a request to request a PD prefix delegation request. This request is sent to the PE. The PE gets the request and sends a radius request to get the prefix which is allocated for this client. The PE here reply with the PD configuration. The CPE receives the prefix, configures the downstream interface, and sets the other bit flag to on, not the managed, but the O bit, which means to the host, use DHCP for other configuration, not to get an address. To get an address, you can use stateless address autoconfiguration, but you can use DHCP to request, for instance, here, DNS server address. So this is a capability which is very flexible in IPv6. DHCP can also be used for some transition to IPv6 protocols like 6RD. 6RD permits to deploy an IPv6 service over an IPv4 backbone, just like 6PE but without MPLS. And the residential gateway, which is a CPE, needs a few information configuration like the 6RD prefix to know which neighbor is in the same domain and which neighbor is outside of the domain. It must also know the boundary relay router to exit the domain and reach another IPv6 machine outside of this domain. So all these informations can be provided by the DHCP option 212. So you got the mask length, the prefix length, the border relay IPv4 addresses, which are usually anycast addresses for load balancing, and the RD prefix to figure out if the destination is local or remote. So remember that once the address has been automatically configured, it must be refreshed to remain in the preferred state. So the preferred timer must be refreshed as well as the valid. And this can be done using Router Advertizements or DHCPv6 protocol. But it must be done, otherwise the address will reach the deprecated and then it will be invalid and could not be used any longer. For the statically configured address, there is no such timer and the address is configured forever. So you must also, you may also have to configure a few timers on the routers, like the array interval or the array lifetime, which means every how long, if you send one array every 5 minutes, or if you send one array every minute, you must set this configuration, and the lifetime, so how long the router advertisements become valid, remains valid to consider a router as a default route. You may also have to configure the managed and the other configuration flag if you plan to use the DHCPv6. And all this configuration can be done on the IPv6 and the prefix configuration set. So remember that to be used by stateless address autoconfiguration, the onlink and the autonomous bits flag must be set. So same for if you want the prefix to refresh the address, and if you want also the prefix to refresh the address, the preferred lifetime cannot be bigger than the valid lifetime. The valid must be larger than the preferred, otherwise it may be an error. If it's not the case, then the preferred lifetime is refreshed and also the valid lifetime. So the rule for the valid lifetime is a little bit more complex, but basically it's as simple. It is used to refresh the valid and the preferred lifetime. The stateless address autoconfiguration prefix are refreshed again each time the workstation receives a router advertisement. So the lifetime, the valid and the preferred lifetime timers are decremented all the time by the system clock. And if it was if the preferred lifetime reach 0, then the address is deprecated. So a router advertisement should be sent before. So which means that you must set the router advertisement interval and the lifetime, and also the values for updating the prefixes as well on a proper way, and this way your address are always preferred and can be used for all kinds of configurations. So even in DHCPv6, it was supported with an option which contains the preferred and the valid lifetime. here is an example how the prefix delegation just updates the prefix which has been assigned. When the timer expires, a renew is sent, and this renew is to ask the server to make the reservation longer, so the prefix will not time out. For the renumbering, we also use the preferred and the valid timers. So basically, this can be used with array and DHCPv6. The old prefix is announced with an old preferred lifetime, so all addresses which are derived from this preferred lifetime are immediately deprecated. And so the hosts have two prefixes, one which is deprecated, which cannot be used for a new connection, and one which can be used for a new connection. So it can remain a few days like this to make sure that all the existing connections may die, and then you stop advertising the old prefix, which is going to completely die, and hopefully the new connection will be used and the old connection will not be used anymore. And if it is done smoothly, then the transition is done without any breakage. So that's an example of such configuration to do such a confirmation, so a change. So basically the preferred timer is set to 0, so immediately all the addresses which are derived from the prefix 2001 db8 cafe 1 are deprecated and cannot be used for new connection, only existing connection. So all the new connections are going to the new prefixes, to the new prefix, and the old prefix is going to die slowly because it has no way to do otherwise. Another very interesting feature of IPv6 is mobile IPv6. With mobile IPv6, you can actually roam and you can actually move from your home network to different locations. You will get a new temporary address for each new location. But for the application, it always appears that you are on your home network. So for the application always sees the traffic as if the mobile node was not moving. So basically, without mobile IPv6, every time you visit a new access network, your applications must be restarted because you got a new socket with a new source address. So the transport layer is no longer valid and the applications must be restarted. With mobile IPv6, you get a temporary address every time you move to a new location, but thanks to mobile IPv6 processing, we will see that the applications still believe that the mobile node has not moved and is still on its mobile home address. There is no other choice. So the mobile IPv6 feature is supported on most Linux platforms. and also on the Mac, because the Mac is a free BSD core, but on Windows they say it is supported for the corresponding node without route optimization, but in this mode it is transparent, which means that actually the node don't see that the mobile node is roaming, so it is fully transparent, and it is in this mode that Microsoft says it supports mobile IPv6, which is, to my opinion, a little bit abusing the people, but that's the way they say it. So how it is working? Basically, the mobile node is moving from the home network to a new network, so it is just flying to a new location, and it acquires a new care of address using stateless address autoconfiguration or DHCPv6. Anyway, this configuration is done exactly as usual, no difference. What is happening next is that actually the mobile node is going to send a binding update to the home agent. The home agent is basically your home router, which has a particular function which supports mobile IPv6, and which is a very important node in the mobile IPv6 architecture. In the binding update, it keeps informed the home agent that the temporary care of address is actually matching this home address. So the home agent do some verification to see if the mobile node is authorized to do this operation, and if it is the right guy, not somebody who is pretending to be and is not. If it's okay, it sends a binding acknowledgement, and a tunnel is built between the home agent and the mobile node. So this is an IPv6 in IPv6 tunnel. It has nothing to do with the transition to IPv6 tunnel, and it is an IPsec tunnel. And basically, once this tunnel is established, the home agent is going to intercept all the traffic to the mobile node. So when the corresponding node is sending some traffic to the mobile node, the home agent is going to intercept this traffic and will encapsulate it to send it to the mobile node at its temporary address, because the corresponding node is sending the traffic to the mobile node IPv6 home address, just as if the mobile node never moved from his home network. So it is sending the packet to the home network just like if there was no change. The home agent received this IPv6 packet. It has a binding table where it sees that the mobile node IPv6 address is actually reachable through a care of address, and it encapsulates the traffic to the mobile node. This is true in both directions, okay? So when the mobile node is sending traffic to the corresponding node, it encapsulates it within a packet it is sending it to the home agent, but the packet inside has the source address, which is the mobile node IPv6 home address, and the destination is the corresponding node IPv6 address. When the corresponding node is sending the packet back, again, at this level, the corresponding node has no knowledge that the mobile node has moved, and the corresponding node needs absolutely no piece of software to support mobile IPv6 at this level. So it is sending a packet to the mobile node IPv6 address. The home agent intercepts this packet and encapsulates it within a tunnel with the destination, which is the IPv6 care of address, and the source is set as well. So at this place, the home agent is really the very important, because it keeps the illusion that the packets are sent to the home network when the corresponding node is sending the traffic to the home network. It encapsulates it to the care of address. And when the mobile node is sending traffic to the corresponding node, the mobile node encapsulates it within a tunnel, and the traffic is decapsulated and sent as if the packet was originated from the home address. So that's actually at this level, again, the corresponding node has absolutely no knowledge that the mobile node is no longer on the home network and don't need any piece of software to do this. But in mobile IPv6, this is something which was not possible in mobile IPv4. We can set a direct tunnel without having to pass through the home agents. So in this case, the mobile node is going to send a binding update to the corresponding node. The corresponding node will have to verify that the mobile node is really the node which it is pretending to be, because for security reason, you understand that we must really be very careful, as the traffic may be transiting with many networks on the internet. So basically, how the corresponding node is checking that the mobile node is the mobile node and not somebody else, it sends some packets to the mobile node using both addresses, the care of address and the home address on the home network. And the mobile node should receive both packets because when it is sent to the home network, the home agent is intercepting the packets and sending it to the mobile nodes through the tunnel. And when the corresponding node is sending the traffic using directly to the care of address, again, the mobile node must be able to get this traffic back. So now, how? Because we don't have the home agent anymore to keep the illusion that the mobile node is still on the home network and has not moved. So how do we keep the illusion? This is thanks to the extension headers, and this is why it is only possible with IPv6 and not with IPv4. So basically, when the mobile node sends packet to the corresponding node, it is actually the source address is the care of address, but in the destination option, it puts the mobile node IPv6 home address. So when the corresponding node receives the packets, it replaces the source address, which was the mobile node IPv6 care of address, with the mobile node IPv6 home address, which is in the destination option. So this is done at the IPv6 layer. It is transparent for the transport layer. It is transparent for the application layer. For the application layer, the packet is coming from the home network. And again, there is absolutely no loss of session. It is still the same, exactly the same address, source address, which is going to be received as if the mobile node was still on the home network. On the other way around, we use another extension header. We use a routing type 2 header. And same principle. The packet is sent to the mobile node IPv6 care of address, but we have in the routing header the mobile node IPv6 home address. And it is actually replaced by the mobile node when the packet is received, and when it is passed to the transport layer, the destination address is the mobile node IPv6 home address. So everything again is one more time occurring exactly as if the mobile node was still on its home network. So that's again thanks to the extension header we can do all this. The mobile IPv6 protocol gave birth to many applications. One is the proxy mobile IPv6 protocol for the smartphone. One is the mobile router. One is the dynamic networks which are built dynamically, discovering neighbor and using mobile IPv6. And also something which is very popular currently, which are the wireless sensors network. These are applications of mobile IPv6. There may be more, but these ones are the most important. So what is proxy mobile IPv6? It is exactly the same thing as mobile IPv6, but all the complexity, which means that IPsec and the mobile IPv6 signaling has been removed from the smartphone. It is actually managed by a network device which is called the Mobile Access Gateway. So the Mobile Access Gateway is using neighbor discovery protocol, very simple message with the mobile node to check its identity and many things, and then it is in charge of doing all the mobile IPv6 complexity. It is managed by the Mobile Access Gateway with the home agent, which is renamed the Local Mobility Anchor here. So we see that we check the identity of the mobile node, then we send a binding update and a binding acknowledgement, but with a P is for proxy, So it is a proxy binding update and a proxy binding acknowledgement, but it is the same mobile IPv6 protocol actually. The mobile router is also actually an application of mobile IPv6. This time it is the whole router which is roaming. And it may have many nodes attached, and all the nodes are moving with the router. So the router can be a smartphone, and you can attach a notepad, a camera, an iPad, and again you will benefit from mobile IPv6, which means that if your notebook is logged in the morning from home with mobile IPv6, you keep the same address wherever you go, and you keep this information, and you can then roam and move anywhere without losing your session, without having to log in again every time you move to another location. Another application is mobile ad hoc networking. This function permits to discover automatically your neighbors and to build dynamically a network which is managed, and this can be very useful, for instance, for a fleet of car police, because they discover their neighbors and they automatically build a dynamic network using mobile IPv6 infrastructure. Very important. And this also gave an idea, what if these nodes have sensors to measure temperatures or anything? And this has started the wireless sensors networks group and applications, and a lot of new protocols have been started to have in very small devices sensors and networking devices which are able to build dynamic networks of sensors, and so these are very small devices, so they may not be able to handle a 128-bit long address, so we could have smaller addresses to manage it, but basically this is a very popular application, and we will see it more and more in the future to enable things that you cannot imagine today, because it is really opening many doors, and it permits to do a lot of new applications that we would have never been able to do with IPv4 NAT and the old addresses we had before. So thank you very much for attending this presentation. If you have any questions, please drop me an email. Visit my blog, and if you want, drop me again an email. I will answer to any email you want, and I will be very happy if we keep in touch. Thank you very much, and bye-bye.